Welcome to the third and last lecture or lesson on analytical skills. Today we're going to focus on graphing and error bars, and in particular the uncertainties of graphs. So by the end of this lesson, we should be able to identify uncertainties as error bars on graphs, identify random uncertainty as an uncertainty range represented graphically as an error bar, determine the gradient and intercepts of a straight line graph. That you should be able to do from what you've done in grade 8, 9, and 10, and 11 mathematics and science. Relate straight line graphs to equations in the form of y equals mx plus c and derive expressions that equate to the gradient and or the y-intercept of their graphs. So this is something that we do in NSC physical science. For instance, if you think of the EMF and internal resistance graphs, where we actually extract the internal resistance by looking at the gradient and the EMF from the y-intercept. We do the same in the photoelectric effect, where the gradient of a kinetic energy versus frequency graph is the Planck's constant, and the negative of the y-intercept is the work function. And then we'll determine the uncertainties in the gradient and intercepts of a straight line graph. So when it comes to error bars, these are bars in the x and y directions around each data point that show immediately how big or small the uncertainty is for that value. And uncertainties can be constant values for every data point and percentage values. And yeah, it can vary from point to point depending upon the nature of the measurement. Either way, an error box is created when there are error bars in both x and y directions around a data point. It's usually a rectangle and often varies in size around every point. So I know that normally at Parklands, where I teach, we will represent this as a data point with a region of uncertainty around it. They're talking about representing it like that. That is also okay. All right, so if we look, for instance, we have a graph here of mass versus volume. That would give us the density. We do this in grade 8. Then if you look at that particular data point, the data point is at 1.2, but now if you look here, the error on each side is 0.5, so the uncertainty is going to be, the mass is going to be 1 for this data point, plus or minus 0.5. So 1 minus 0.5 gives us 0.5, 1 plus 0.5 gives us 1.5. So this is the region of uncertainty. That is the error bar in the independent variables direction. If now we look at the mass and we see that we have a variance of 1.2 is the mass, and the error in this direction is 0.1, because it's 1.2, 1.3, 1.4. So this is 0.1 and that's 0.1. Then we can see that the mass, the uncertainty is plus or minus 0.1 gram. So when you have data like this, we have time here, which has an uncertainty of plus or minus 0.1 second on either side. The positions are 1.9, 3.1, 5.5, 8.2, etc. And what we find is that the uncertainty in each of the positions varies here. So it looks like it's a percentage error. So you can actually see here that as you plot these error bars, we can see that in actual fact the length of the error bars in the vertical direction actually varies. So if you have a percentage error, the bigger the value, the bigger the error bars are going to be, and you can actually see that in the dependent variable. You can actually see that your error increases. So now, when we plot a line of best fit for data, all right. Now in the NSC syllabus, we talk about a line of best fit. Some people would say it's a trend line if you don't work it out using linear correlation, right, or least regression. But we are going to work with this being the average line. That's the line of best fit, and it's going to have a gradient m. Right, then when it comes to drawing the maximum gradient line, we are going to take the lowest value, the lowest point, and the highest point, right? And so what we're going to do, we are going to go to the bottom of the error bar in the vertical direction of the lowest point, and we're going to draw a line from there all the way to the highest point, and we're going to go from the lowest point's lower error bar value to the highest point's highest value in the error bar. So that gives us a maximum gradient over that data set. Likewise, when it comes to the minimum gradient line, we're going to go to the lowest point. Now we're going to go to the upper, to the highest part of the error bar vertically and connect it to the lowest part of the error bar of the highest point, and that's going to give us the minimum gradient. Right, so let's just do this again. Let's just review this. Calculating the uncertainty range of the best fit line requires the steepest and the shallowest gradient. The steepest gradient is drawn from the lowest possible value, that's the bottom of the error bar, to the highest possible value, top of the error bar of the highest point. The shallowest gradient is drawn from the largest value of the smallest value, and these two gradients are then calculated and compared to the best fit line. So now we're going to work with percentage uncertainty, and I'm going to do an example with you. So if we take that same data, and now we work with the line of best fit, we choose 2 points. I'm going to call them E and F. Right, E is going to be 2, 3.6, and F is going to be 6, 11.6. This is 10, that's 11, that's 12, so we're 11.6. All right, then when we work out the gradient of the line of best fit, it's going to be y2 minus y1 over x2 minus x1, which gives us 2 meters per second. So you can see this is the average gradient because that is the gradient of the line of best fit. Then, when we want to work out the gradient of the steepest slope, then we get 2 points. We've got A, let's see, A, which is 1.8. And I'm actually looking there and I'm realizing that that actually looks like a mistake. That should be, this is 3.6, and this should be 1.8. Apologies for that. That should be 1.8. Okay, let's do this. So this should be 1.8. 1.8. Right. Okay. So this is 1.8. That's a point on the steepest slope, and 6, 12.8. So when we come up to here, it should be 12.8 minus 1.8. 12.8 minus 1.8. Just going to take this out. All right. Over, we're going to have 6 minus 1. So that's going to change that value. So what are we going to get there? 12.8 minus, just get this. 12.8 minus 1.8 is 11. So that's 11. divided by 6 minus 1 is 5. And that's going to give us 2.2. So this is going to be, apologies for that, this is going to be 2.2 meters per second. Right, so that is the maximum gradient. You can see it's got a higher value than the average gradient. Now we're going to go to the minimum gradient line. Okay, and I've drawn this in green. Right, so this point here is 1, 2, that's point C. Point D is 6, and it is about 10.3. That's 11. 10, 11, that's halfway, it's 10.5, it's 10.3. All right, so now when we work out that gradient, right, 10.3 y2 minus y1 is 10.3 minus 2, 10.3 minus 2 meters. X6 minus 1, which is 5. So 10.3 minus 2 divided by 5 gives us 1.66 meters per second. So just looking at those values, you can see the steepest gradient line has got the highest value, the minimum gradient line has got the lowest value, and then the average is in between, which is what it should be. So now when we work out the percentage uncertainty, we take the maximum gradient minus the minimum gradient divided by the gradient, the average gradient. So this shouldn't be 2.4. This should be 2.2. So I'm going to put that in. That should be 2.2. 2.2 minus 1.66, which is the minimum value, divided by equals divided by 2. And that gives us 0.27 times 100. That should give us 27%, not 37%. That should give us 27%. There we go. So now note that using significant figures, minimum amount of significant figures here was 2. So I only used 2 significant figures there. Right, so that was calculating the percentage uncertainty in the gradient. Now, when it comes to calculating the percentage uncertainty in the y-intercept, we work out the y-intercepts of the different lines. Remember, the blue line is the maximum gradient line, so C should have actually called that C2, right? Doesn't matter, in line with what I had before. Doesn't matter. This is the y-intercept of the maximum line, gradient line. This is the y-intercept of the minimum gradient line, and that is the y-intercept of the average line. Now note that unfortunately these y-intercepts go below 0. All right, and we don't have a grid there. So if that's 0.4, that's about minus 0.4, that's about minus 0.5. So taking maximum minus minimum, but it doesn't really matter because we can actually use absolute values here. Really doesn't matter. It's a magnitude we're looking for. So if we take that, we've got negative 0.4 minus C2, negative 0.4 minus C2, negative 0.4. All right, we're going to get negative 0.8 over negative 0.5. You take the signs away, and you get it's 160%. That is a very, very big error. So this spread here is bad. So not good. All right, but that is the method. Okay, so take a look at exercise 6. It says here, exercise 7. Rearrange each of the following equations into the straight line form using the red quantity as the independent and the green quantity as the dependent. So here we want to linearize these equations into a y equals mx plus c form. So we basically want we want y equals mx plus c. So I would like you to give these a try. Pause the video, give them a try, and when you've done that, don't do this yet. When you've done that, then take a look at what I'm about to show you. Now, you're going to pause, you're going to do it, and then you can look at the answers. Number E is really challenging because it involves logs. I don't know how much logs you've done. By now, you should actually, grade 12, you should have done logs. We're going to use the natural log. So try and use the natural log. That's really a tricky one. And the number 2, elastic bands are used to shoot an arrow off in the water at different initial velocities. The time taken for the object to come to rest is measured. Use an equation of motion and a knowledge of straight lines to determine the acceleration of the arrow if the gradient was determined to be 4.5. So my advice is first do these. Look at what I've done. I'll then ask you to pause. Then do that one. Look at what I've done. Pause. And then do that one. Right. So you pause now and you give 1A to D a try. Okay, so let's take a look here. So we want to make V the subject of the formula. Well, if you want to write it in y equals mx plus c form, well, there's your x, there's your y, and that is your m, and that is your c. Now, you might be saying, so why don't you square root it? Well, if you square root it, then you don't get a y equals mx plus c form. Right, so your y here is the velocity squared. Right, if we look at this one, this comes from the photoelectric effect. So this is the maximum kinetic energy of an emitted photoelectron. That is the wave function of the metal, and that is the incident photon's energy. So we are going to make the green, V squared, the subject of the formula. Right, and the frequency is the x. So take this to the other side. So we're going to halving V squared equals HF minus W0. All right, if we now divide times by 2 all the way through and divide by m, we get that V squared is 2h over m, f minus 2w0 over m, y equals mx plus c. All right, this one you also know. This is the EMF equals the internal resistance times the current. This is the lost volts plus the operational voltage or the external voltage across the external part of the circuit. So we want to make I the subject to the formula. IR equals, take the minus V to the other side, plus EMF, and now we divide by the internal resistance. I equals minus 1 over RV plus EMF over R. Y equals mx plus c. This is a trickier one. This comes from thermodynamics. Q over delta T equals Ka over L delta T. We want delta T to be the subject, so we're going to times by L and divide by Ka on both sides. This K here is actually sitting upstairs. It's actually sitting in the numerator. So when you write a K like that, the K doesn't belong to the numerator and the denominator. The K is actually K over 1, so it's Ka over L. So we times by L and divide by Ka, so it's Q times L divided by delta T Ka. But the A now, remember, is in red. So we want the A as the independent variable, but now it's downstairs, so we make it 1 over A. So this is y equals mx plus c. All right, so how about giving this one a go? This is a real toughie. Challenge for those who are comfortable using logs. So if we look here, this is actually the decay equation for radioactive decay. So this is N is the number of undecayed particles in a sample. N0 is the original amount of particles, radioactive particles that were undecayed. 1 over T, the tau is the half-life, and T is the time at a particular point in time. So pause the video and give it a go. So what I did is I divided by N0 on both sides. The t is our dependent variable, so I've linned both sides, logarithm to the base e. Right, I've logged both sides. Upstairs to downstairs law, minus t over tau, I'll bring downstairs. Ln e is 1 because it's log e to the base e. All right, I got minus t over tau times by negative on both sides. All right, and then I times by tau. So now I get t equals negative tau. I use the quotient subtraction law. So ln n minus ln n 0. Multiply 3 by negative tau. Now what I do is I bring this to there. So this is y equals mx plus c. But now your x is the natural logarithm of n0. Okay, it's quite a tricky one. Okay. All right, so with the elastic bands are used to shoot an arrow off in water. Pause now and give that one a go. All right, use an equation of motion, your knowledge of straight lines to determine the acceleration of the arrow if the gradient was determined to be 4.5. Pause and give it a go. So I've used, if we plot a graph of t versus vi, t is the time it takes to come to 0, and vi is the initial velocity of the arrow leaving the elastic band. So v final is v initial a delta t. Delta t is t minus 0. V final minus v initial is a t. Now v final is 0 because remember, this arrow is going to come to rest. So negative v initial equals a delta a t. T is your dependent variable. So we make t the subject of the formula by dividing by a on both sides. So t equals negative 1 over a v initial. All right, we're working with y equals mx plus c. The gradient is change in y over change in x is 4.5. So this is y equals mx plus c. So your m is negative 1 over a, which is 4.5. All right, so negative 1 over a equals 4.5, which means timesing by a and dividing by 4.5, a equals negative 1 over 4.5, which means a is negative 0.222 meters per second squared. Why is it negative? Because the arrow is being decelerated by the hydrodynamic drag of the water on the arrow. So, this is a nice application of graphs. Now, here's an exercise for you. Determine the percentage uncertainty in the gradient and the y-intercept of the following graph. What you have here is you have graph of quantity A versus quantity B. Quantity A versus quantity B. You have a set of data points with varying uncertainties. You have varying error bars. Quantity B ranges from 0 to 8, and quantity A from 30 to 35. Determine the percentage uncertainty in the gradient and the y-intercept of the following graphs. I leave that as an exercise for you to do. I will post the solutions of this together with the notes of this lesson. Thank you very much. And with this lesson, I end off this section on analytical skills and scientific method to my grade 12s. This is your last official lesson, content lesson. I wish you well. You might still have some revision lessons, but for the time being, we're done with the syllabus. May the force be with you, and all the best with your preparation for your exams. Thank you.